doing that, I would like to know how many people are actually listening. I see how many people are on Zoom, but is that the number? Are people locally in the room too, or how are you doing right now?
So locally in the room, we have about 30 people. Yeah, you can have a look at the camera with the camera. So you can see all the hands.
Yeah, I can.
Yeah, so you can see the hands, I guess, right?
Okay.
Hands. And we have 17 participants online also. These are the
I see those.
I hope you can see them. And we have 17 people online also, which includes you and me. So 15.
Yeah. Okay. I have just lost the window where my presentation is running. It's behind something else. So unfortunately, I have to give me a moment until I can close down everything else and find where it's hiding.
Yeah, no problem. No problem.
Because I thought I'll start that before and then it went somewhere.
So let me use this time to introduce Moritz to everyone. And Moritz is at MIT. He's been working on Chandra Data for a long time, right? 15 years, probably 10, 15.
Yeah, for a while.
Yeah, for quite a long time. And so today the session which we are having is on installation of Ciao, which is the software which is used for Chandra data analysis. And today Moritz will show us how to install the software. And then we'll have a follow-up session on Sunday, which will basically be a tutorial of actually using the thing. So in case people do not manage to install the software today, do not worry. You have the whole of Saturday to try to install it. And then on Sunday, when we have our session, you will actually use the Ciao you install. So welcome, Moritz. Thanks for joining us, and over to you.
Yeah. Let's see. I thought I'd do that quite a little bit different than what you just said. So I'm going to tell you a little bit about why we might want to do Xray astronomy at all. Right, we are going to, in the second session, we are going to reduce some Chandra data and do some Xray astronomy visit. But I first wanted to convince you that Xray astronomy is actually useful and we can learn something from it. And then I'll walk through the steps that we'll do on Sunday. And at the very end, I'm going to tell you how to install the software. And so my goal is that by the end of today, you know how to install the software and you know roughly what steps to expect. Like what they mean, how we reduce Xray data, what it's good for, what the data formats are. So that when we do that on Sunday, I just need to tell you what to type essentially to make the software work, but you already understand what it's good for. That's my goal. But first, I think I should tell you what Xray astronomy is actually good for. Because if Xray astronomy isn't good for anything, then analyzing some Chandra data wouldn't make any sense, right? So I've selected a couple of examples. I've selected examples that look good, where the images look good, or I've worked on myself. Xray astronomy is a large field. It's there's certainly over 1,000 astronomers working on Xray astronomy. So maybe not as many as are using optical telescopes, or not as many as are using infrared telescopes. But it is a sizable community. There's major observatories, and so there's a lot of things observed from planets to the Big Bang. You can essentially see anything else in between in X-rays in some way. And I want to give you some specific examples, some examples I handpicked, what it's good for and what we can learn from X-rays. This is the Earth. So the Earth itself that you see at the bottom, I should check. Can you see my mouse pointer? Yes. If nobody says something, then I assume you can see my mouse.
Yes,
thank you.
Yes.
So the Earth image is, of course, the Earth image, but then these color things here, those are observed by an X-ray observatory called Chandra, which is the one I work for. And what you see there is the Earth aurora. The North Pole is up here, and the charged particles that the sun emits in the solar wind, like hit the upper layers of the atmosphere of the sun. Of the Earth, sorry. They hit with high speeds and high charge. They hit the upper layers or close to the pole because they have charged particles, so they need to follow the magnetic field lines. They hit close to the Earth's pole and excite oxygen, ionized oxygen in this case, likely to make like oxygen 6 or oxygen 7, highly ionized oxygen. And that's what you see here through charge exchange glowing at the Earth. And the observations are taken over a couple of days, like whenever Chandra had a chance to look down. And you see that it's like, yeah, it's close to the North Pole, it changes in shape, it changes in structure. And while I don't work from that, we can learn something actually about the Earth and the Earth's magnetic field. Almost all our planets, or many of our planets, show X-rays, although they're faint. On Saturn, we see actually the reflection of solar X-rays. Saturn itself doesn't seem to make X-rays. On Jupiter, you see a similar thing as I just showed you on the Earth. You have like these the picture of Jupiter is from Hubble or something, but these purple, that's where the X-rays are. And so similar to the Earth, Jupiter's magnetic field directs the solar wind to the North Pole and the South Pole, and that's where you see the magnetic, that's where you see the X-rays come from. Then for Venus, you see fluorescence, like the sun shines on Venus. Venus is very close to the sun, right? The X-rays from the sun shine on Venus' surface, essentially on Venus clouds, and the oxygen in the atmosphere gets excited and fluoresces. And what you'll also see when you look closely at all these images is that often in X-rays, we don't see things terribly well. So every individual yellow dot here is an X-ray. We count individual X-rays. On those images for Saturn and Jupiter, it's smoothed. So it's like the image is processed, but this is a photon, this is 2 photons, this is 1, this is 1, this is 1, this is 1, and I think this is 8 or so. So we often don't have a lot of photons, and that means the techniques we use and the things we look at when we actually look at the data are a little different than what you would look at an optical image. Like if you take an optical telescope and you only catch 8 photons, 8 pieces of light, then there isn't terribly much science you can do with that. But in X-rays, you can. Okay, here's something that I worked on before and that I've worked on, Priya has worked on when she was visiting us at the Harvard Smithsonian Center, although not exactly this image. This is the so-called Pillars of Creation in the Eagle Nebula. And the background image is from HST. So what you see in HST is all these dust formations, these dust structures. And in these dust structures, in these little globules at the front, there's young stars forming. But we can't see those that are still deeply embedded in the gas and dust. And so a question we would like to answer is this all the young stars, or has this thing evolved and are there maybe young stars like in the middle here? And because they're so shiny, like you might imagine that, for example, this star or this one, some of the bright stars that they're so bright and that's what evaporates this cloud here and makes these shock fronts on the side. And so we need some method to identify the young stars here too. If you look at the optical, there's just a lot of stars and you can't say if they're old or young, but young stars are X-ray active. And so when you look with Chandra, you get these point sources. Those are X-ray images overlaid with the color, shows you the energy of the X-rays that we observe from that individual star. And so that way we find stars as we find stars even at large distances. This is kiloparsecs away. So you also see that the images are not as nice and point-like. They're not as, the resolution is quite as high as HST. I'll show you a little bit about that later. Here's a pure X-ray image, Cassiopeia A, supernova remnant. And so in X-rays, what we do is we detect, for every photon, I said we often count individual photons, although this is a very bright object with millions of photons, but we detect individual photons. And for every photon, we know more than somebody who would take an optical image. We know where we detected it, obviously. I mean, it's not much point if you don't know where your X-ray comes from. We know at what time we detected it. That's not terribly helpful in this image either, but we also know what energy every single photon has. And because we know what energy it has, we can look in the spectrum and think about or learn what element it's coming from. And so the red image here is a silicon line. And so that's a supernova explosion. The center of it sits somewhere here, and then it explodes. And you see there's silicon over here. And in particular, there's this outflow that's mostly dominated by silicon. And then you have iron. Iron comes is high, bright in these clumps here. And then the green, this outer shell, only this silicon plume goes through. In green, this outer shell, you see the continuum shock. So that's the outer gas that runs into the interstellar medium and heats it up and shocks it. And so these are highly energetic processes. This stuff is hot. This is millions of Kelvin hot. And it's a gas that we can essentially only find in X-rays, and only in X-rays can we do these measurements of the abundances in this very hot gas. Here's another one, the Crab Nebula, which looks good. This is combined from Chandra, Hubble, and Spitzer. And you see here, Chandra is this purplish bluish in the center. And you see that it's a larger nebula. There's a lot of structure and cavities and stuff. And the inner cavity, that's filled with X-rays. And that tells us that this inner cavity is filled with hot gas of several million Kelvin. And the gas that fills these cavities outside is significantly cooler. So we can use the X-rays to measure the temperature and to identify where the hot gas sits. A famous image, these are all galaxies very far away. Most of them are so far away that they just look like dots. It's called the Chandra Deep Field Norse. Here's some active galactic nuclei with jets like that come out on the side, and you can measure those jets. And those jets, and some of those move with like half the speed of light or something. And because they're so fast, when they run into things and they're strong magnetic fields, again, they shine in X-rays. And without X-rays, we probably wouldn't know very much about these jets. You see some of them in radio too, but as you often see different components. You see like the outflow itself and the X-rays, for example, and the shock in the front in radio. So that gives you different pieces of information, and you really want to use both Chandra and radio observations to learn most that you can. Here's a galaxy, a whole galaxy. This is again an image just in X-rays. And so this white circle that marks the position of the galaxy, it's roughly a galaxy that we're looking on kind of a little bit from the side, which is why it has this shape. You see like that's brighty on the center, and imagine it like a large spiral that sits in here. And so you see that the galaxy itself is brighty in the center. That's probably an active galactic nuclei. But you also see this hot wind that comes out here on the side, or this hot gas that's dripped from the center of the galaxy. Probably, I'm sure people have looked at that. I don't work on galaxies myself, and I don't know much about this galaxy in particular. But that's probably as the galaxy moves through the intergalactic medium that it kind of gets, some of wind gets stripped behind it. And again, the color tells us something about the temperature that the X-rays have. And so the elements or the temperature of the gas that it comes from. And so you can go and measure the gas, and you can measure how much there is and estimate how much gas the galaxy loses. And those processes matter because when you strip out gas and dust from a galaxy, then, for example, the galaxy can't form stars any longer. But on the other hand, you put like processed gas that comes from the inside of a galaxy where supernova have happened, where iron and other elements have been formed. That's not just the Big Bang nitrogen and helium. You put that into the intergalactic medium. And so you have hot gas that can, for example, absorb stuff that comes from behind you, that comes from the other side, right? Or if, let's say, if this was a galaxy behind it, stuff would be absorbed and you would see absorption lines. And so that matters if you want to know how much mass is there in the universe. The Big Bang model tells you what our cosmology is. We have like an expanding universe, we have dark matter, we have dark energy, and we have normal matter, and we want to measure how much there is. And if you don't look in X-rays, if you just look in the optical, you're not going to see this gas, and you'll forget counting it because it really only shines in X-rays. Okay, here we go to the larger scales. This is a galaxy cluster. So every dot that you see here is a galaxy, or sometimes maybe even several galaxies. So this is really far away, right? It's close to the edge of the universe, so to speak. It's thousands or possibly tens of thousands. I don't know this particular cluster, and I'm not very good in remembering numbers like J0717.5, right? But this cluster has thousands of galaxies, and the white image is a Hubble image. And so for some of them, you see this is like a spiral galaxy. For some of them, you can make out shapes. And this purplish is a smoothed version, like a washed out version of what Chandra sees. And that's So the X-rays. And so this is the cluster center. And you see that because galaxies, like in this galaxy cluster, the galaxies are moving around and the galaxies are hitting each other. And like I showed before, they're stripping hot gas and they run into each other. And so in the center, this hot gas collects in the center. And this hot gas provides some pressure because it's hot that stops other gas from the outside, for example, from falling into the cluster. And there's cooling flows and mass flows within those galaxy clusters. So if people who study like the evolution of galaxy clusters want to see this hot gas. We can do more with X-rays. Like I've shown you images before, but we have on 2 instruments, on Chandra and on XMM Newton, we have high resolution spectrographs. And so we can do detailed spectroscopic studies like people do in the optical or in the infrared, right? And so this is a spectrum of AB DAW taken with XMM, the the European X-ray mission, with its RGS instrument on the XMM telescope. And this is an emission line spectrum. It's from AB DAW. It's a close by active star. This green dotted line is roughly like a continuum. So that tells you how hot the corona is. The corona is the region that our sun also has. It's a region around the visible star, like the photosphere itself, the thing, the red glowing or yellow glowing thing of the sun is around 6,000 Kelvin. And after that comes a corona, a very thin gas that's so thin that in optical light, we don't see it at all. But in X-rays, it's very bright because it's a few million Kelvin bright. And so we can measure what this corona is made from by looking at these lines. And this line, which is the brightest in the spectrum, that's oxygen 8, sorry. And over here is oxygen 7. And so the ratio of oxygen 7 to oxygen 8 tells us something about the temperature. If the gas is very, very hot, if the gas is cold, oxygen is going to have a lot of electrons. And as you heat up the gas, like the oxygen atoms and the hydrogen and the electrons that are on there, that bump into each other and they strip the electrons off the oxygen. So as the oxygen gets hotter, as the gas gets hotter, it's more and more ionized. And so at some point, you reach a temperature about a little under 1 million Kelvin. Then most of the oxygen is oxygen 7. And then as it gets even hotter, that oxygen 7 that bumps into more electrons and another electron is stripped off that oxygen and it becomes oxygen 8. And as it gets even hotter, most of the oxygen 7 disappears and most of it becomes oxygen 8. And so by looking at how much oxygen 7 we have versus how much oxygen 8 we have, we can measure the temperature of the corona of that star. And similar, we can look at, for example, neon 9 versus neon 10, or we can look at iron. And we can look at which elements we see at all and which we don't see. So here's oxygen, here's iron, here's another oxygen, here's neon, here's magnesium. Now, XMM isn't very good at like these short wavelengths. So there is actually silicon and magnesium. We just don't see it very well because XMM is not very sensitive in this region. But from doing that and from fitting that and analyzing that, we can learn about the elements in stars. And so we are not going to look at a spectrum like this on Sunday because we only have 2 hours and are a little more complicated. So I've picked a slightly simpler example, but we are going to look at stars, at spectra of stars. And we are going to look at what elements are in those stars on Sunday. We are only going to, because the spectra I've selected to play with are not as good. We are probably only going to see like neon at all. And the rest we won't be able to see. But if you had a close by bright star, this is what it would look. Here's a zoom in for different star on EQPAC on just this small region here, the oxygen triplet. And I've selected this because that's something that I've worked on myself. And so what you see here is that there are 3 lines next to each other. This is the so-called R line, the resonance line, the intercombination line, and the forbidden line. Now, those lines have different upper levels. They're excited in different ways. And so if you have a very high plasma and a very high density, for example, because stuff falls onto the star, as it often happens in young stars, then this I line becomes, this F line becomes weaker and the I line becomes stronger. And so by measuring the ratio of these 2 lines, we can't just say it's oxygen and we can't just say how hot the oxygen is. We can also say how dense the gas is that we see. And another thing that you see here is you see like these individual bins with error bars on them. This is a very, very well exposed spectrum. And even there, you see that this black line, the fit of the spectral shape doesn't fit perfectly well. There's all these noise up and down. And that's because we often just don't have that many photons. Okay, so I know I want to get to how we reduce X-ray data and how we install Ciao and what it's all good for, how we do that. But I wanted to convince you that analyzing X-rays actually makes sense. With X-ray sources, we often see hot, like a collisionally excited gas. Let's say I've wrote over 5 megakelvin. We'd also see 2 or 3 megakelvin gas, but we see like the very hot gas that's often difficult to see in other wavelength bands. We see fluorescence from iron. We see Bremsstrahlung from fully ionized gas. We see non-thermal electrons, like from non-thermal processes, strong magnetic fields, like jets that are at relativistic speeds, like 0.2 or 0.5, the speed of light. And often those are things that are very energetic, they're very fast, and they're often hard to see in other wavelength bands. Okay, so how we go? How do we actually see that? Now, we are fortunate that there's a number of instruments, but they're all in space because X-rays from the sun, right? I know you are astronomers, so maybe I don't have to say that, but something that I'm often hearing is that people think we X-ray the stars, like the doctor X-rays your hand. That's not the case, right? We're using observatories. We're observing the X-rays that are coming from the universe anyway. We're not sending any X-rays out. But because the X-rays can't make it through the air, we have to observe them from space. Fortunately, they don't go through the air because otherwise we'll all die of skin cancer if we were constantly bombarded with X-rays. The disadvantage is that building X-ray telescope is relatively expensive because you have to put them on satellites and send them up. And the 2 biggest ones that are currently in orbit and have been both since 1999, the workhorses of Xray Astronomy are Chandra, which is a NASA-led mission, and XMM Newton, which is an ESA-led mission. Those are still both functional. They both have some smaller problems, but they mostly still work after 25 years or so, or almost 30 years in space. Almost 25 years in space. And they both have well-developed software and well-developed archives. And I've just to work with one, I've picked Chandra because the software is a little easier to install and I know it better. But they're very similar, in fact. And then there's a number of smaller missions, like India, for example, launched AstroSat. Germany and Russia have launched eROSITA, Spectrum X Gamma, which is the one down here, where eROSITA is currently not operating because of the Ukraine war. The Germans and the Russians have stopped working on it together. NewStar is a telescope that's made for higher energy X-rays, that even harder. NISA is an instrument that's mounted on the International Space Station that's very good for things that change very fast, like fastly rotating neutron stars, for example. So there's a couple of these smaller specialized instruments. But fortunately, essentially all of them use the same format of data. And the analysis steps for all of them are very, very different, or essentially the same. So I'm going to pick Chandra as an example. But after I've told you how to reduce X-ray data, and we've worked through that in one example, or a Chandra example on Sunday, you should be able to do that. You should be able not do it right now. You probably still have to read the manual, right? But you're going to understand the steps, and you should be able to reduce data from all of these. Okay, so how do we do that? We are going to use a software package called Ciao. That is software specifically written for Chandra data analysis. So it has a number of things that are specific to Chandra, and it has a lot of things that work with any X-ray data because they're using the same format. So you'll do the Chandra specific steps first, and everything that comes after those specific steps, you could equally well do on XMM data, or NewStar data, or on AstroSat data or something. So there's essentially 3 softwares that do similar things. There's Ciao, there's SAS for XMM, and that again has a couple of XMM specific steps, and then everything that comes after the first few steps could use SAS for any X-ray data. And then there's a software called HiaSoft, which contains of the so-called F tools, and that's what many of the smaller instruments use. So it's like a little bit more general, but again, like you could use, once you have done the instrument specific calibration, you could use any of those for any X-ray file. Most of this collaboration, most of these standards and these file standards go back to ROSA, like in the 1990s, and have essentially every instrument since uses the same type. It's all FITS files, although we don't always call them FITS files. They're all FITS files, and they're so obviously FITS files that you don't even have to say .fits. We all know we are talking about FITS files anyways. And then there's different types of FITS files that have a specific type of data in them. And I'll show you one in particular in a second. I want to point out, though, that both Chandra and XMM in particular have spent a lot of effort on making it easy to find and analyze data for people who aren't typically or don't often do X-ray analysis. In Chandra, we call that the Chandra Source Catalog. The version 2 that's been released last year has over 300,000 X-ray sources from everything Chandra observed prior to 2014, and now we are slowly adding newer data sets. The astrometry, the position is good about 1 arc second. It has X-ray photometry in different bands. And it has all the data products that we'll need to, for example, fit a spectrum, and I'll show you later or show you on Sunday. And so you can just go and download anything. Anything with Chandra that's been observed more than a year ago is free and open to the public. And specifically, if it's in the Chandra source catalog, you can just go and essentially download it and write your science paper right away. For grading data, I showed you the high resolution data. We have a specific grading data catalog. That's I'm advertising that because that's my group. That's the group I work in that does that at MIT, and that's like at this web address. And if you Google Chandra TGCAT or gradings catalog, you're going to find it. And you're also going to find it from the Chandra website, so you don't have to write that down. But all gradings data ever taken has been fully reduced, and so you can go and just download it from there. Again, we're not going to do that in the example because that'll be a little boring if everything was already done, right? We're going to start from scratch. Okay, the fundamental data format we have to deal with, the data format you have to mostly work with in X-rays, is called an event file. In optical astronomy, you have images. That's even if you take a spectrum, really what you do is you disperse your light and then you have a camera, and that camera takes an image. And you start with that image and do things with it. In radio astronomy, it's a visibility array. And in X-rays, it's an event list. An event list is a table. And in principle, you can use Google Sheets or Microsoft Excel to do X-ray astronomy. I say in principle because our event lists are saved in FITS file, and I believe Microsoft Excel can't read FITS files. But if you take some program and convert it from a FITS file to a CSV file or something, then you could do X-ray astronomy in Microsoft Excel or on Google Sheets. Why do we do that, or what do we do? So an event list is a table of photons, and for every photon, there's essentially 4 things. There's the X and Y position, let's say on the detector on the sky where that photon was detected, the time when it was detected, and the energy that it had. So the way, like, you can close your ears for the next 30 seconds if you don't care about the details, but I think it's useful to know. The way most of these detectors work is in Chandra, for example, that we take an image every 3 seconds or every 3.2 seconds. We take an image of the entire detector. But typically, in that entire image, there'll be only 5 photons. And Chandra is far away from the Earth. So we don't have the capacity, the antennas can't transmit enough data to transmit the entire image to the ground. To transmit one 3.2 second image to the ground takes about 20 minutes. So we can't transmit every image because we take one every 3.2 seconds, and we have to wait 20 minutes until it's on the ground. That's clearly a giant waste of time. And most of those images are empty anyway. There's going to be like 3 dots and many millions of empty pixels. So what instead happens is that on board, there's an algorithm that detects at which point there is actually a photon. And instead of sending the entire image that's mostly empty and has 5 dots in it, it just sends us the location of those 4 dots. The X and Y location, the time when that image was taken, and the energy for every individual photon. How do we get the energy? Well, when an X-ray hits the CCD, it hits the photon, then because it's so energetic, then the detector is made of silicon, it kicks electrons off the silicon atoms. And we essentially just count the number of electrons. And the more electrons we find, the more energy that photon must have had. So what we actually transmit down is the number of electrons. And then you can multiply that by some number, or software does that and converts that into an energy. In detail, we transmit a couple more than those 4 parameters, because these electron clouds, they often hit more than one photon at one pixel at the same time. So you don't have to transmit just 1 pixel. You transmit like 3 times 3 pixels, like the one in the center and the surrounding ones. And that helps you to distinguish between X-rays and background events, like protons that come from the sun, for example, would also hit that detector, or cosmic muons would hit that detector. And they make a different shape. And hopefully, or most of them make a different shape. And so you can distinguish real X-rays from that background by looking at what shape they make in the 3 times 3 pixel island. So in reality, we transmit a little more. But in practice, like, all you need to know essentially from an event list is an X, the Y, the time, and the energy. And here's an example for such an event list. This is from observation 26133. That's the observation ID, and that's the one I'm going to use for the example on Sunday for me. There's actually millions of events, but in order to make them fit my screen, right, I've just printed the first 15 here. The first row is the time, and you see in the region I cared for here, the time goes in steps, and I said, like, if you look between rows 7 and 8, you see that it's gone forward by 3.2 or 3.4 seconds. So the first 7 photons here were detected in the first 3.2 seconds, and then the next ones are detected in the second 3.2 second image. But instead of sending an image that's 1024 times 1024 pixels to the ground, we just have to send these 7 rows of information to the ground. And so here's the time, here's the position in X, Y in a coordinate system that's centered on some point, like the corner of the detector or something like that. I'll show you in a moment how we deal with that, and that it's not terribly much of a problem, because the Chandra software can convert that into a RA and DEC, the right escension and the declination that you usually want. But this is how it comes in X and Y. And here's the energy in electron volts. So this first photon had 11.153 keV, 11,000 electron volts. And so I can, from looking at that, I can see that that's probably background photon, because Chandra's mirrors don't actually focus X-rays that have that high in energy. And that means it's almost certainly not a real photon. Here's another one, 12,000, 10,000. Those we can take the software and we can say, oh, that's more than 10 keV. Chandra can't really see more than 10 keV X-rays, so those must all be background, and we'll just throw them away. These 8.8 or 8.59, 9,000 EV, like 9.6 keV or 9.7, those are probably also be background events, because again, I know that Chandra's mirrors can't actually focus X-rays very well that are this. And I know we are looking at a star, so stars are not that hot. So if I go through here, of all these photons, of all these 15 photons I put in here, like this is the only one here, number 7, that has like 2 keV. So that's likely or possibly coming from a star. Could also be a background event, I don't know, but that could be from a star. So you see there's still some background in it that we have to deal with. But that's what an event list looks like. Okay, so what we can do now is we can bin this event list. We can, for example, bin it in time and say, in the first time bin, there'll be 1, 2, 3, 4, 5, 6, 7 photons. In the second time bin, there'll be 1, 2, 3, 4, 5, 6, 8 photons, and then like we keep counting, and then we get a light curve. Or we can take the X and the Y and say we are making a grid of X and Y, and we just count how many photons we have in every pixel, and then we get an image. Or we do the same in energy and say how many photons do we find at each energy, and then we get a spectrum. And so here is one, not the list I showed you before, there's a different target. Here is one that I've binned in energy. At the bottom is the energy in keV, and I've like simply counted all the photons between 1 and 1.1, 1.1 to 1.2, 1.2 to 1.3, and so on, and put them in bins. Now in this particular case, and that's what we often do in X-rays, I haven't actually made the bins the same size. I've made the bins wider or narrower so that I have at least 15 or 20 counts in each bin. because otherwise it's just very noisy and goes up and down. And then that red is a model that's fitted through it. So this is the iron line here. This is silicon emission. This is neon emission. But we can't see that yet. But you can see that by making a list and binning it in energy, we get a spectrum. Now, I said this red thing is the model, and I'll get back to that in a bit, how we do models. I can bin it in time. I can just count how many photons do I have in time. So here's one where let's look at the right side first. This is a star. This is also a star. They're flaring stars. So you see, like in kiloseconds, we often measure the time in kiloseconds in X-rays because that's what you do, grams and kilograms, seconds and kiloseconds, meters and kilometers. So 80 kiloseconds, 86 kiloseconds are 1 day. So this is a little bit longer than 1 day. Okay, and you see, we've just we've just counted how many photons did arrive in the first 1,000 seconds, in the second 1,000 seconds, in the third 1,000 seconds, from 4,000 to 5,000 seconds, and so on. And this is just the number of counts per second. So in the first 1,000 seconds, if I get 100 counts, then I get on average 0.1 counts per second. And so I put a dot here. And so I do that, and you see this giant flare. So what happens there is the same thing as in the sun. We observe that in the sun too. It's like this is the quiescent emission, and then a magnetic field on the star. Some two magnetic field lines reconnect, and they accelerate electrons to be super fast and hit the ground, hit the photosphere, and it rises up, and then it slowly cools down. Okay, this on side, this image is a different way of expressing the same thing. So this is the Orion Nebula cluster. It's observed for almost a month. And we have we've made an image. We have put all the photons that are observed in the first, let's say, 10,000 seconds. All the photons that are observed in the first 10,000 seconds, we've put on this XY grid. And that gives you this image. And then we've done that with all the photons in the second 10,000 seconds and so on. And then you get a movie. And you see that the stars are flaring, they're sprinkling on and off. And it's actually color coded here by the energy of the photons. You see that as stars flare, they often become hotter. The flare goes on. I'll run it again in a second. There's stars coming and going. There's some stars that are always bright. And so for this movie, we've used the X and Y position. That's how the photons got in the image. We've used the time. That's how we made it a movie. And we've used the energy to put the color on. So that's all the information we have from a photon. Here is a similar thing, except for this observation. It's all photons that are observed over all times, but at different energies. And so it says in small here, the 0.5, 0.5 to 1, 1 to 1.5. And we've made a series of pixels, a series of images similar to in the optical and the infrared, people would call it an IFU, an integral field unit. In X-rays, you do that all the time. And we've done that for 30 years, and it's nothing special. We do that because we don't have images. Again, we have an event list where we know a lot about every photon, the X, the Y position, the time, and the energy. And you see that there are certain structures here, this extended emission that's only seen at low energies, but it's not seen at higher energies. Okay, so I've talked a lot about the event list, and that's because we are going to do a lot about the event list. I just want to summarize that there are a couple of things that are different in Xray astronomy than you might be used to. We count photons, and because we have so few photons, we often need to worry about statistics well, right? Because, yeah, I'll come to that in a second. I'll show you that our lines are often a little messy, and so we do modeling a little bit different. We often have pretty broad bands that are like a decade in energy from 0.1 to 2 decades in energy from 0.1 to 10 keV. And that means that the detector, the optics, the detectors, they react very different to 1 than to a 10 keV photon. And so things like if you do, let's say with HST, you take a filtered image, it doesn't really matter if you take a red filter, like a photon at the low end of the red filter band versus the high end of the red filter band, there really isn't much difference. But in X-rays, because these filter bands we use are often so wide, that makes it matter. Okay, our optics are different. Like we often have, specifically in Chandra, it looks very good in the center of the image and then becomes blurry on the outside. Whereas in Hubble, for example, you get the same resolution all the way through. And specifically, Chandra again moves on the sky. It doesn't point on the same position. I'll show you in a second. But we do have for every photon, we have the XY position, the energy, and the time. Okay, this is a summary of the steps we do. And I'll just show you that as an overview of colorful images. And we'll go through the individual steps. So this is what you get directly from the telescope. It's called a level 1 event list. There's some stuff has already been done to it, but there's clearly dirty stuff that happens on here. You see like these bright strips over here. Those are bad columns where something in the electronics on the detector doesn't work out. You see these like things, these shiny things here. Those are hot pixels, where 1 pixel on the detector always gives you a signal if there's a photon or not. These are node boundaries. There's a separate electronic that reads out this half of the chip versus that half of the chip, and funky things happen at the boundaries. And there's lots of background here. So we take this level 1 event list, right? So this is an image I've made from knowing the X and Y position of every element, of every photon. But we know more, right? I said we know the energy. For example, we can throw away everything that's above 10 keV because we know that to be background. We can throw everything that sits on a pixel that we know to be hot. And when we do all those things, we end up with what's called a level 2 event list. So we filtered things, flipping back and forth to the same data. You see, we've filtered out these bright columns. And what you get, though, then is like when you look carefully, there's a little data missing from these bright columns. But you see there's like a black strip now, but we don't have as much because we had to throw away data. Then you still see sources here. You see a lot more sources than you saw before because we've thrown out a lot of background. You see that sources, these are all points. The source is further away from the center. The center is here. Sources are small. Out here, they're a little bigger. The next thing we need to do, or we need to take care of, is that Chandra doesn't actually point at the same position at all times. Chandra, what we call dithers, that means it moves in this peculiar pattern, a Lissajous pattern over the sky. So the same pixel, the pixel 5, doesn't always point to the same position on the sky. But for every photon, we also know the X and Y position on the chip, and we know the time it was detected. So we can calculate what pixel number 5, what that is in Ra and Dec on the sky at any one time, because we know this pattern that Chandra has. And that's called an aspect solution. Almost all X-ray telescopes have that, although Chandra's looks a little more funky than most. That's called an aspect solution. And so there is a step that we need to calculate for every photon based on the CCD XY position, what that actually is on the sky. Okay. So again, this is a zoom in. You see the point sources. This is what you get after every photon is shown in the Ra Dec position where it is. And you see that here between the pixels, between the chips, there's still a little bit of data. And that's because most of the times this is between the chips. But because Chandra moves over the sky, sometimes even this region is observed by Chandra as this chip moves a little bit up and down. So what we get in Chandra is we have like this cross pattern, but we still get a little bit of signal everywhere, just a little bit though. And so what we do is we make an exposure map that's like in sky coordinates. So this is in a Ra Dec. You see there's real coordinates at the bottom here, 00, 51 minutes, 23 seconds. How many seconds did Chandra actually look at that? Because it moves around. And you see these strips here. This is between the chips where it only looked very shortly, as it like only at the very corners of this movement pattern got some chip on here. And you see like these rows of bad data that we blocked out, which effectively means like not much time there was a working chip that looked at that. So that's what we call an exposure map. If we plot it in raw coordinates, you see like this is in chip coordinates. And because Chandra moves over the sky, the source is now smeared out a little. And that explains why we do that, because sometimes the source hits like these like white strips that we have to throw out because they're bad. And so without that dithering, there would be a risk that a star, for example, just happens to sit constantly on a region that's bad. But because we move around, everything will sometimes be in a bad region of the chip and sometimes be in a good region of the chip. Okay, I will have to torture you with a formula. This is the only one I'm going to show. I'm going to show it twice though. It's like, fortunately, we don't have to ever calculate this by hand. but it's useful to know what is meant. Okay, so we observe the sky S, and the sky has some position, latitude and longitude, which I'll call X and Y, and photons come from that at some time t with some energy E. But that's not the same as what we see, because what we see, we count a number of photons, but things have happened in between. For example, the telescope doesn't detect every photon. Like some photons just hit a speck of dust on the mirror, or some photons hit a chip gap, or some photons just don't get reflected because mirrors aren't perfect, and some photons are absorbed. And so there's a difference between the true number of photons that come from the sky and the number of photons n that we actually observe. And so that's called the sensitivity, is what fraction of the photons that come from the sky actually make it through the telescopes, through the mirrors to our CCD. And what also happens is that the mirrors aren't perfect, right? So even if a star is a point, sometimes it doesn't get reflected perfectly. It gets reflected a little bit to the side, and you get like the smeared out position. Or sometimes the detectors count the electrons, but they don't count the electrons perfectly. Some electrons are getting lost, there's some noise. And so the number of electrons we detect isn't exactly the energy that that photon had originally. It's close to, but there's some distribution around it. And that's what we call the response R. So the observed number of photons is, mathematically speaking, an integral over what truly comes from the sky, integrated over what our telescope does in the effective area, how big our telescope is and how much it makes it through, and how that stuff is redistributed. That's why we call it response. How the true energy E maps to the energy that we actually detect, and the true position maps to the position that we detect. That matters a little bit. Now I'm going to take this equation, I'm going to write it a little simpler with a little fewer things in them. Because when we do spectroscopy, these parts are stored in different files. And so it's useful to know that these files exist. So we observe is that n is the observed number of photons, and those we stick into a file that we call a PHA file. And those are FITS files, even though it's called .pha here, is that we know everything's a FITS file, so we don't say .fits every time. What that is it's our event list. It's the number of photons for, let's say, for this source, all photons observed in this region, and then binned in energy. That's the PHA. And this is what we want to detect, the true model, the true distribution of photons. And so we need to multiply it with an ARF file, or integrate over with an ARF file. And the ARF file is made, you need to make that ARF file using a command. You need to calculate it because the effectivity of the telescope changes with time as dust and dirt collects on it, even in space. And so that's calculated, and that's called the ARF file. And this response is called an RMF file. And we also need to make that, and I'll show you in a second what it looks like. And then we need to know the time t, which is the time, how long the exposure was on. So we integrate over t, we assume everything is the same. So we can pull that integration out, and then we integrate integrate dt, and then we end up with t, just the time, how long the observation lasted. And that's stored in the file header. It's called the lifetime. And so we integrate over x and y for making a spectrum by just taking all the photons that this source sent here. Like we make a little circle, like this is over background, but we say all the photons in this little circle come from this star. And so we integrate over x and y. Integrating just means we sum everything in that circle. And so we've summed over x and y. So now we only have to worry about that e. So we have this function here. We can pull that t out. But that's what we call forward folding. So what we do is we take the model, we take a model for the star, and we do this calculation and compare that with what's observed. That's a little different from what you would do in the optical typically. In the optical astronomy, when you have, let's say, a spectrum, you would say, oh, the spectrum has a resolution of 10,000. And now let's go and measure the equivalent width of a line or something. We say, here's a model, let's multiply it with a function that has gives every spectral feature the same shape that's observed in the telescope, and then we compare it to the data. So it's subtly different, but that it is that way because we often have very few photons. Okay, I want to show you how these individual elements look like. The point spread function is the spatial response that we'll try to integrate over that. And that means how much does a point get smeared out in the image. And this is from Chandra, like the center is very bright, and then as you go outer, it gets fainter and fainter and fainter. And at some point, we're going to have to cut off because it never gets to zero. It just gets fainter and fainter and fainter. But if you go too big, then we get all these background photons. So what we're going to do is we're going to put like a circle around it, let's say like here, and say this circle has 90% of the light. And then we multiply by 1 over 0.9, we multiply by we lose 10%, we do all our measurement, and then we add 10% back in. We know that 10% are the photons that we didn't see because they're scattered so far away. Okay, for energy, an ideal detector would give us for a, I have the zoom bar, I have to zoom bar, move the zoom bar out of the way. An ideal detector for a photon of 2.65 keV would detect all the photons at 2.65 keV. But unfortunately, that's not the case because the detector isn't perfect. There's a little bit of smearing out. And so a photon, a real photon that has 2.65 keV could also be detected as 2.5 or 2.55 or 2.6. And that's what's called the response matrix function. So what we do is if we see a photon that has 2.5, we detect it at 2.5. We don't know if it really comes from 2.5. It could be a 2.5 photon. It could also be a 2.65 photon that just got scattered or got smeared over here. So what we do is we do a model over all energies and multiply it by this function. And then we say, oh, if we smear this model out, does it look like we observed? If we smear that, take that model and smear it out, does it look like what's observed? If you take that model and smear it out, does it look like what's observed? And then we find the model that smeared out with these RMF looks closest to what we observe. This is the effective area. It just tells us at which energies we see things the best. And when we put it all together, here is again that data that you saw before with a model underneath. And this red line is a smeared out model. The true model, the true model looks like this. But because of this RMF, all these really sharp emission lines from certain elements get smeared out until it looks like that. And that's why we do this forward folding, this smearing out, this trying a model and smearing it out. This is an image of the Chandra PSF. As I said, if you go further away from the center, it gets smeared out and looks a little worse. And sometimes for really bright sources, you also get fancy, funky stuff like these streaks or these spikes or something. You don't have to terribly much worry about that for the sources we look at tomorrow, but you should know that it's there and that sometimes you see things. There's other instrumental effects that we aren't going to go through in the 2 hours we have tomorrow on Sunday. Okay, one thing worth knowing though is that we often have very, very few photons, and that's why we have these really large error bars, right? And so we have to worry about statistics, because if you observe, if you have 10,000 photons, then you can assume that the number of photons that you draw randomly from a true observation is Gaussian distributed. So if you have 10,000 photons, there's going to be an error of 10,000 plus minus 100 or so. If you only have 2 photons, right, you might be saying, oh, let's say we have 4 photons. Right? If you do 4 photons, the 1 sigma error on that is 2. So it'd be 4 plus minus 2 photons. Now, what's the 3 sigma error on 4 photons? If the 1 sigma error is 2, the 3 sigma error should be minus 2 to 10. Now, we are never going to see minus 2 photons. And that's why Gaussian statistics doesn't work here. What we need is a statistic that's called Poisson that takes care of things that have very few counts in them. And in order to do that, we have to compare to the observed photons, which is why we don't why we need to have like the number of photons in each of these bins, and why we do take the model, multiply it with all this stuff to make it look like the data, as opposed to taking the data and dividing it by the Blaze curve, or so as an optical astronomer might. Okay, I'm through with what I wanted to tell you about analysis. We're going to do that in real on Sunday, and most of these steps the software will do for us. But I want to make sure that you know what these things are. When I say take a PHA file, take an event list, look at the event list, that you know what these things are. A summary: X-ray telescopes drift, so we need to take care of the aspect solution, or the software does. If you have very few photons, you need to worry about the background and the statistics. The properties change with distance to the center and with energy. I explained this forward folding. But once you've learned it, because it's very, very well standardized, you can essentially just take all of the data from all the archives and start doing science. Okay, what we are going to do is we are going to observe Chandra data. And Priya may have sent you my email already, so you don't have to type this off from the slides now. You can copy and paste from the link that you have. Because obviously, like typing something off, it's easy to put a typo in there and then it won't work. I've picked Chandra partially because Chandra's the Chandra software can be installed with Conda. And I know that many of you are working with Python and are familiar with Anaconda or with Mini Conda or Conda Forge or some of those things. So if you have Conda on your computer already, and you're running a Mac or Linux, because there's no X-ray reduction software that works on Windows, then you can essentially just copy and paste this command. The first part, the Conda subtier here, you only need if you're running on a new Mac with an M1 chip. Everybody else, if you bought a MacBook in the last year and you have an M1 chip, you probably know about it. If you don't know about it, you don't need it. Then we call Conda, we create an environment that has a new Ciao version in it, and these are the packages we want to install in that. I've added AstroPy in the end because I like it, and AstroPy is useful for lots of things in astronomy, and so it's nice to have in the same environment. You can add other things. It's not technically part of Ciao, but I think it's useful. You should know that the Chandra calibration data, these ARFs that's needed to make these ARFs and ARM-Fs, is a little big, because by default, you're going to install all the calibration data for all Chandra observations ever. The good thing is, if you have enough space, if you can do a 2 GB download, if your internet is fast enough for a 2 GB download, and you have 5 GB of space or so on your hard drive that you can use for that, then you take this command as I've wrote it, and that includes the CalDB, the calibration database, and you'll never ever have to worry about not having the right calibration data, unless you look at data that's observed in 2024, then you should probably update your calibration data, because we don't know yet what the telescope will look like in 2024. But for all previous data, you're going to be fine. And so if you have that space, the easiest is to install the CalDB. If you are really short on space on your, and you can delete it, of course, if you on Sunday afternoon, right? If you need that space back. If you don't have that space today, you can leave out this CalDB main. That's going to save you most of the download. After that, it's a few hundred megabytes. And so your Wi-Fi will thank you, because it's going to be a lot faster to download. But then we'll have to manually download the calibration files that you need for your example on Sunday. So if you have space, just throw it in and then you have it. If you don't have space, we'll deal with that on Sunday. So I would like to know who of you has a Linux, or maybe the other way around. Who does not have a Linux or Windows computer, Linux or Mac computer? How many people have Windows and no Linux on the same computer? I see one.
Yeah, there's one person on the chat window. There are a few people. What could be a quick solution for them?
For those, you are essentially out of luck for any X-ray astronomy. For those of you who are local, I suggest that you find somebody and pair up in a team of 2 on Sunday. That's why I'm asking now, so that you can worry about worry about who you team up with, and you just sit in front of the same screen and run through the same example and share typing. If you can find somebody, that would be great. An alternative is, and I'm not saying that you necessarily need to do that, because if you don't need it otherwise, it's a lot of work, right? But you can install a Linux on a Windows computer. There is distributions like Cygwin that kind of make a computer in your computer that you can even start from a USB stick if you have one. So you don't have to put it on your hard drive. You can install Cygwin, or you can use the Windows subsystem for Linux. However, for the one person who are remote, and I wasn't fast enough to read off your name, I just saw your hand going up in between. For the one person who is remote, unless you're really into computers and you want to try that, my suggestion is that on Sunday, unless you want to do with Xray data, and you need to figure it out, right? If you don't want to deal with Xray data, my suggestion is that maybe you just look on Sunday, as opposed to spending a lot of time on a system that you may not need. I'm not sure if you're allowed to unmute, because I think only co-hosts are. But you can probably press a button. If not, send me an email and we'll try to work it out. But for a 2-hour tutorial, making a 2-hour installation first doesn't necessarily seem terribly useful. So I'm glad it's only one person. I'm sorry. I'm sorry for you. But there is no Xray software for Windows. We can't do anything about that, really. Okay. For all others, for all people who do have a computer, please take the link. Don't type this off. Like, take the link that you have, and try to do the installation. Maybe when I'm hanging up in 2 minutes, or tomorrow morning. Send me an email, like, if you run into any problems. So I should say that there is detailed installation instructions on this link that are a lot more detailed than this. If you can't solve it, specifically for the people who are in person, talk to those people next to you who have already solved it, and send me an email. That's why I give this talk now, so that you have a day to work it out. I do know, though, from other workshops that we have done, if you all do it at the same time, it's going to take a long time. And that's because this CalDB download is like 2 or 3 gigabytes. And so if 50 people at the same time try to download 3 gigabytes, that's 150 gigabytes, and your Wi-Fi will go down, or your Wi-Fi will take a while, right? That's why we do it now, so that you can do it. And if it takes a while, if it takes a while, that's not a problem. Okay, I see there's more things in that chat window. Let's say Windows. Okay, that I didn't see that fast. Yeah, the Windows subsystem for Linux. Somebody said the Windows subsystem for Linux should work. I just don't have a Windows computer, so I can't try out and give you exact steps. But if you run the Linux subsystem for Windows, that's Linux enough. It should work in there. Again, for a 2-hour tutorial, if you run into a problem, it might be easier for those local people at least to pair up with somebody. Okay, I'm almost done. I want to prepare you for one more thing. And that is that Ciao, the Chandra software, and also the XMM software and other softwares are traditionally used from the command line. So people will go on the command line and type things in, like this: dm copy 26133 repro. You see this thing here. This is real data analysis. This is from the lines that we do tomorrow. There is another way, both for Ciao and for XMM. There is a Python interface, so you can do it from Python and from a Jupyter notebook. And you see, like, it looks almost the same. dm copy. This is actually identical to this purple one. This orange one is this orange one here, which I've put into quotes, but apart from that, it's the same. This clobber yes, okay, becomes clobber true, because in Python it's called true and false and not yes and no. Right? This line, dm extract, is here. This white thing is exactly here. This one is here, except that it's in quotes. This one is here, except that in quotes. This one is here, except that yes becomes true. So I'm going to use on Sunday, what I'm going to do is I'm going to send you an IPython notebook where some of this, since we only have 2 hours, some of the stuff is already filled out and looks like this. If you go off and look at the documentation, you'll find examples like this, but you'll see that they're almost identical. And after tomorrow, you can probably translate from one to the other. So what we'll do on Sunday is I'll give you this notebook with some things pre-filled, and then we'll do one step. I'll show you one step for one data set, and you'll pick some data set, some other data set, and I'll give you a list of data sets that are similar. So we all run into the same problems and our data looks similar. I give you a list of data sets which are similar. Every one of you picks one. Everybody has a different one. Everybody's going to analyze their own star. We'll see how many of those stars we cover. Everybody measures one star, and then at the end, we'll hopefully get the average temperature of X-ray emission from stars by comparing all the stars that people look at separately. But so you'll follow the same notebook, but you'll always have to fill in the details for your star. And I'll do one step, and then I'll wait for you to like say okay, or put the thumbs up or share your screen or something until most of us follows, and then I'll explain the next step, and we'll do the next step. I will also use this link and forward it or ask 2 or 3 more people from the Chandra X-Ray Center to join me for Sunday morning, which for us is Saturday night around midnight in Boston. And so there'll be 2 or 3 more people, not mine, but 2 or 3 more who join us. And so you should feel free, if you run into any trouble, to use that chat window. And even while I'm talking, there'll be at least 1 or 2 other people who can answer questions when you run into something in the chat window. So if you run into trouble, I'm also saying that if you run into trouble, if you run into installation trouble, try it out now and email me and follow the instructions. If you run into trouble on Sunday, or we still haven't worked installation by then, use a chat window and we can like try to solve that. Some of us can one-on-one. Somebody asked for my email. I believe Priya has already, or should have, Priya either has already or will very shortly send you a link to the installation instructions, and my email is on that page. I can type it.
I sent the link, but not the email. I'll send it.
The email is at the bottom of that page.
Yeah, I know that, but I didn't share it. Yeah, okay, I'll share it. No problem.
I mean, it's here, but at the bottom of that page that Priya sent you, and that I can send you to, at the bottom of that page is my email address too. Give me a second to change to my web browser. I have that.
It's there in the chat window, so people can cut paste it from there. Anyway, I'll send it in the mail. No problem.
Okay, so the link that you have should get you to this page. It's on GitHub, and I'm going to put the notebook that we'll use on GitHub too. And all the links I showed you before on here. This gets you to the official documentation on how to install things. If you have Conda, like the official documentation will tell you to just take this. If you're willing to install AstroPy too, you can, or any other thing, SciPy, whatever you want. NumPy comes with it, but SciPy, okay, like stats models, whatever you want in your environment, you can type any other thing behind here that Conda knows about. I like AstroPy. If you're on a Mac, you'll also have to install Xquartz and have to have Xcode. It's explained on this link. It's entirely possible that you have that already. And if you're on a Mac with an M1 chip, as I said, then you need to put this before. If download volume or disk space is a concern, leave out the CalDB mean. So you essentially do what you do before, but you delete this part. And then it's going to look like this. Any problems? Here's my email address. Here is the official address of the help desk, and you can just write one or both of us. And we'll see what we can do and we'll try to get, it's usually fairly painless, but we'll try to get you all on before Sunday morning. Okay, please go and install and let me know if you run into any problems.
Yeah, so thanks so much, Moritz. That was a lovely session. And I think now people have a lot of work to do trying to install that. So I think we'll hear from.
If you have Conda, and you have enough disk space, you're on Linux, you'll be done in however long it takes its download. It's just one command. If you're on Mac and you have Xquartz and Xcode, which many of you may already have, then you're also going to be done in one command. So I hope that most of you will be done fast. But if not, let me know if you run into something.
Yeah, sure. Sure. So thanks a lot, Moritz. That was really very nice. I think you can hear the applause.
Yep, I can. And I'll see you on Sunday.
Yep. So see you on Sunday. Bye-bye. Bye. Yeah. So tomorrow we start at 9 a.m. IST with Timothy Hamilton on integral field spectroscopy. 9 a.m. IST. Right. Tomorrow morning. See you. Okay. Okay. Thank you.